Good morning, everyone. We're Rocket Project, and my name is Jesse. I'm the propulsion team lead.
My name is Yuan. I'm a structure team's lead.
My name is Michael, and I'm on avionics.
So the purpose and motivations for our team project is to design and build a Rockoon, which is essentially a rocket-powered balloon. And we want to use this to study the mesospheric part of the atmosphere. Additionally, in order to make this possible, we have to strive to make sure that there's an active stability system for the hosted rocket. In order to even get that high up and possibly even send it into space, we also need to make it an efficient liquid bipropellant engine. And I'll get to the reasons why later, but essentially we need to do groundbreaking development for a new type of engine here at UCI in order to achieve our desire for possible CubeSat space launching. And so our team structure is split up into 3 teams, as we formally introduced ourselves. Michael here is in charge of avionics, Yuan here is in charge of structures, and I'm in charge of propulsion. So as a team, as a general team, we meet bi-weekly. We discuss past and future and present tasks at hand. Sub-team meetings for our individual teams are held every week before and after the general meetings. And in between then, we try to make sure that we consolidate all our information on a Google Drive, just Google Drive. So our current mission and budget. So the primary goal for avionics is active stabilization, engineering control using fin systems. As propulsion team lead, our current task is to design a high efficiency liquid bipropellant rocket engine. And for structures, it's a rocket powered balloon, or Rockoon, which is meant for high altitude studies. Using the member fees as well as the UROP funding, we have $3,700 to use as a team. We have a prioritized budget for each of the individual sub-teams for our overall team, and that dictates how much each team gets and what gets purchased first. So typical problems we will run into going forward through the development of our rocket. First one is drift of the rocket. Second one would be stability in terms of center of gravity and center of pressure. Efficiency, so engine performance primarily, losses due to drag and propellant utilization. Fabrication, so a lot of the fabrication done for the rocket can't be done here on campus strictly because we need a high tolerance or high level of accuracy for a lot of the engine components. And then cost, lightweight materials, very expensive, fuel, very expensive, and as I previously mentioned, machining, very expensive. So I'll hand it over to Michael, who will introduce avionics.
Okay, so as Jesse said, our primary goal for avionics is a active stabilization. In order to achieve this, we have to derive the roll control laws. We have to CAD the airframe and size the internal design. And we're fabricating a small rocket to test our control laws and our algorithms. Essentially the goal is to each sub-team achieve like a milestone, and then combine, next year's rocket project would combine all of our milestones into a larger rocket. So even though the propulsion's rocket is much larger than the avionics rocket, they still should fundamentally work together. This is a picture of our current design, and the way we're going to achieve the control is through actuating the fin tips, and these are going to be actuated by small hobby servo motors. Okay, in order for a rocket to be stable, the CP has to be behind the CG, typically 1 to 2 diameters, and we're going to try to go like half a diameter to 1 diameter, because we want it to be stable but not too stable. So if it's too stable, our stabilization system essentially it's non-effective. So we don't want it to be too stable. So the reason for this roll control is basically if you don't have control, the rocket flight path, the rocket can deviate from the desired flight path, and this can have undesirable effects. This is going to be the microcontroller that we're using. Typically, most projects will use Arduino. This is actually a parallax propeller. And the main difference being that this one has 8 parallel processors. So since we have multiple sensors, as you can see they're listed here, we have an accelerometer, gyroscope, altimeter, and also the speed, and the microcontroller has to power the servos. So by having 8 parallel processors, it's easier to accomplish this. Now I'll hand it back over to Jesse.
So I'll be going over what the propulsion group essentially has been taking care of for the past year. So when you look at a rocket engine, there's a lot of subject materials that come into play: chemistry, thermodynamics, fluid mechanics, and then structural mechanics. And all of those combined essentially give you an effective means to designing an engine. So for our engine, at least this year, we're focusing on designing a liquid oxygen kerosene powered rocket engine that's meant to provide 1,000 pounds of thrust. And then to better quantify that, 1,000 pounds of thrust can probably lift 2 motorcycles pretty high. So it's going to be UCI's first liquid rocket engine, and it's going to be one of the strongest liquid rocket engines made in California, if we can get this done. So in terms of goals for this year, first off, we have to fabricate the actual engine itself. And that includes CAD models, getting the design ready, machining the chamber, the combustion chamber and the injector plate, and then cold flow testing. And I'll get to that in a bit, but essentially that's what the primary fabrication entails. So in order for us to actually test this engine, we can't build a rocket, put the engine in, and launch it simply because there's a high risk associated with that. So what we're planning to do is carry out a static test fire. And in doing so, that's the primary goal for our team this year. And what we're going to rely on is a test stand fitting at the Friends of Amateur Rocketry in Mojave. They'll be providing a test stand for us to mount our engine on and do thrust measurements, and also a way for us to make sure our engine properly works. So when you look at an engine design, or a liquid rocket engine, there's 4 major components: the combustion chamber, the nozzle, the injector plate, and the ignition system. So as of right now, we have the nozzle, the injector plate, and the chamber well on its way to be completed. And our final design looks a lot like this. So what you can see is the ignition system with A&N Army Navy fittings, which is going to be supplied by solid grain ammonium perchlorate fuel propellant. That's going to be used to ignite the liquid oxygen and kerosene impinging in the chamber, which is going to be fed out through the graphite nozzle. So the nozzle's been already taken care of, the injector plate's being taken care of, and the combustion chamber's already been taken care of, as I mentioned. So here's a brief CAD model, or some CAD models of our injector plate and our nozzle. So our injector plate consists of 4 major plates that are used to flow both the kerosene and the liquid oxygen together. And you can see there's a series of orifices as well as stagnation pools for the liquid to rest in. And once it's ready, once pressure fed, it'll be fed through the streams and impinge in the combustion chamber. The nozzle, on the other hand, we couldn't use aluminum because aluminum is not going to withstand the 3,400 degree exhaust plume, and that's in Kelvin. So a lot of materials melt. So what we use is a carbon-enriched graphite, or a silicon-enriched graphite, I'm sorry, to design our nozzle. And this is going to be a reusable graphite nozzle that's going to be inserted to the combustion chamber. And currently, I personally designed that, and that's meant to perform 3 full times at burn times of 45 seconds or more. To put that in perspective, most amateur rockets only burn for about 20 seconds. So this is built to operate at a very high performance tolerance and for a very long time. As I mentioned, with the help of Mr. Colin Sledge, we had our injector plates fabricated or 3D printed, and they're now currently being cold flow tested. And essentially what that means is we're supplying a liquid, typically water, through it to check and make sure all the impingement streams and channels are correctly functioning. The nozzle, like I said, has been professionally manufactured, and that's also ready to go. So overall impact of the propulsion group. As I mentioned earlier, this is going to be UCI's first liquid rocket engine, and we want this to be reusable going down the future for younger UCI Anteater rocketeers to take over for us. So the entire engine, as I showed you, is extremely modular. You can take it apart, switch it out however you see fit. A simple design allows for future development for future UCI rocketeers. It's cheap, so our overall budget for this engine is well under $1,000. The parts that I showed you surmount to about $860 altogether. The only cost that really worries, or the only major cost for the engine itself, is the propellant, so the LOX and kerosene. We haven't been able to find a cheap supplier for that, but we're looking at anywhere from $400 to $600 for the propellant. combined, so liquid oxygen kerosene. Lastly, this is going to be UCI's future liquid engine platform going forward. I'll hand it over to Yuan for structures.
Okay, so for the structure teams for these years, we will finish 2 designs. So for the Raccoon, we have 2 balloon stations. One is the solar hot air balloon, which is only require the solar energy. And the other solution is the helium balloon, which we need to purchase a lot of helium. So we will finish 2 designs. And for the first design is the helium balloon versus Raccoon. So we will build 2 prototypes for it. The prototype 1 will be a small-scale model just for the structure testing. And we will only test it at low altitude. And the prototype 1 is just like this size. And the prototype 2 will be a large-scale model for the recovery system testing. And we will actually launch it to around 65,000 feet. And the prototype rocket will be launched at that altitude. And our second goal is to design and fabricate a solar hot air balloon version. Because of the weather in Southern California, it's very hard to achieve enough temperature gradient in a solar balloon. So we will only test small-scale models to test the structures. And our third goal is to design and fabricate a small prototype of ram air parachute precision landing system. One of the disadvantages of the Raccoon is the drift problem. Since it's very hard to steer the balloon during the ascent, we decided to steer the parachute during the descent. And this precision landing system can bring our platform and the rocket back to the launch site. And with the Raccoon, initially it's a balloon-topped rocket. The rocket will be carried by the balloon to a high altitude, and the balloon will be the rocket will be launched at that altitude. And by using the balloon, our rocket can pass through the dense atmosphere before the ignition. And it can reduce the cost of atmosphere research a lot, especially for the mesosphere. And if this concept can work, we have the possibility to use the Raccoon to launch a satellite. And this is our design for the solar balloon version. For the solar balloon version, we only use one single solar balloon because the single balloon design is the most stable design. And we fabricate the solar balloon by ourselves. And so we can easily to integrate the balloon with the launch structures. But for the helium balloon design, we decided to use multiple balloons because we can now easily integrate the commercial weather balloon into our structures. But for the disadvantage of the multiple balloon is that we cannot make sure the buoyancy force in each balloon is equal. So the platform might be tilted a little bit. So we designed a gimbal system to stabilize our launch pad. This is a gimbal system. So you can see wherever the platform is low, the rocket is always straight up. So the launch pad will be stabilized. And we also designed a lightweight windshield to block the sudden gust. If there's a wind in this direction, the rocket will like this. But if we have the windshield, the force will be transferred to the platform. And this is our prototype rocket that will be used to test the recovery system. And this rocket will be launched at 65,000 feet. And this is our timeline. My team and the propulsion team basically finished the design, and we have already started fabrication. And the avionics team is doing almost finished design. So we will start the testing at the early spring. Okay, that's our project. Any questions?
Thank you.